Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 10 in our Circuits 2 Electronics lecture series, where we continue our discussion of RLC circuits and second order circuits, basically. So at the end of the previous module, we got to a point where we were able to determine the output response of our RLC circuit for the overdamped, critically damped, and underdamped cases. And that was fine. I mean, we talked about the equations and hopefully that all made sense. But I think it's also important to just spend a little bit of time and talk about physically what's going on in the circuit, because we saw kind of a lot of new and sort of unusual things, particularly the underdamped case. So in the underdamped case, this was the first time we actually saw oscillations in our transient response. And it's worthwhile talking about where those oscillations come from. And in particular, something that maybe some of you will have picked up on when looking in the previous module is that when we looked at the output voltage as a function of time, we have our 3 volt level. And in the overdamped case, we sort of asymptotically approached that 3 volt level. In the critically damped case, we asymptotically approached it a little bit faster. However, in the underdamped case, we shot right over it and then sort of came back and oscillated and then finally converged to 3 volts. And so, I mean, one place we can start our discussion is to say, well, where the heck did this really high voltage level come from? Because our input is just a 3 volt step function. So we only have a 3 volt supply in our circuit. There's no other voltage supply in our circuit. So how is it possible that we can generate voltages greater than 3 volts? Well, the secret is actually thanks to our inductor. So in the underdamped case, we have a relatively small capacitor compared to the size of our inductor. And a small capacitor will charge quickly. And so when we switch in our 3 volt source, we get some current going through our loop. And that current is going to be, fairly significant, and we're going to charge this capacitor fairly quickly. And so before very long, our output voltage starts to approach 3 volts. So we start and we charge a lot faster. And you'll have seen this in the underdamped response, right? Like our voltage shoots up much faster in the underdamped case than it does for the critically damped or the overdamped case. And so once we hit 3 volts, why don't we just sort of flatline here and stop? Well, it's because of the inductor. Remember, inductors will try to maintain current flow, and they resist instantaneous changes in current. And they will actually generate voltages to keep current flowing just the way it was before. And so we've got, a current flowing around in the clockwise direction. Once our output voltage hits 3 volts, so we've got 3 volts across these two terminals, we've got 3 volts across these two terminals, and there should no longer be any current flow. However, the inductor says, well, I kind of like this current flow. I don't want it to stop. And so it actually creates a voltage across itself that will add to the source voltage in order to keep the current flowing in the clockwise direction. And so it will essentially add in series to the input voltage and will produce a higher voltage across the capacitor, and will basically overcharge the capacitor. And so that's why our voltage keeps on shooting up, up, and up. So why do we eventually stop here? Well, it's because the inductor can only maintain that voltage for as long as it has energy stored in its magnetic field. And so as it continues to push current onto the capacitor, it depletes the energy stored in its magnetic field to the point where it can't maintain the voltage anymore and the current flow stops. However, at this point, we now have an overcharged capacitor. So the capacitor is charged at a voltage that's higher than 3 volts, so it can actually discharge current back into the circuit in the counterclockwise direction because its voltage is greater than the 3 volts of the source. And so then current flow will reverse through our circuit. It'll move in the counterclockwise direction, and as a result, the voltage starts to drop because the current flowing in the counterclockwise direction will take charge off the capacitor plates, and then the voltage will start to drop across the capacitor. So we now have current flowing in the counterclockwise direction. And then the voltage continues to stop or to decrease, and then we hit our 3 volt point. And then the question is, well, how come why doesn't our voltage just stop? Because the voltage across these 2 terminals and these 2 terminals is the same. It's the inductor playing a role again. The inductor has gotten used to having this counterclockwise current flow, and it says, hey, I don't want this current to stop. And so it will induce a voltage across itself, but this time it will have the opposite polarity. And so what happens is this voltage will actually over-discharge the capacitor and cause the capacitor to dip below 3 volts. Eventually, when the inductor runs out of energy in its magnetic field, it will stop. The flow of current will stop. However, the capacitor now is undercharged, right? It's below 3 volts. And so now this is the opportunity for our source voltage to start pushing current in the clockwise direction again. And the cycle repeats. The question is, though, how come we see, when we looked at the underdamped case, we saw that the amplitude of these oscillations gradually got smaller and smaller and smaller until they leveled off. The culprit there is the resistor R. So every time we push current through a resistor, it dissipates energy in the form of heat. So it actually steals energy from the circuit. And so the capacitor and the inductor are kind of exchanging energy back and forth, but every time they do that, current has to flow through the resistor, and there's a little bit less energy to share back and forth. And so that's what causes the exponential, or sort of the decay of the amplitude. So that's the underdamped case. And we'll come back to this notion of kind of the capacitor and an inductor sort of tossing current back and forth between themselves when we talk a little bit about oscillator design near the end of this module. But let's now talk about the overdamped case, right? So we talked about the underdamped case. We know why there's oscillations. Why are there not oscillations in the overdamped case? Because surely the inductor is going to want to keep the current flowing, so how come it doesn't always bounce back and forth between the capacitor and the inductor? Well, in the overdamped case, the capacitor is really, really large, much larger than it is in the underdamped case relative to the size of the inductor. And that means that the capacitor charges a lot more slowly, and the voltage increases, much more slowly because of that. So we know an inductor, the voltage across the inductor is related to the rate of change of the current. And because we're charging so slowly here, and the current is changing so slowly, the inductor doesn't really have the ability to generate a large voltage like it did when the current just shot right up, as it did when the current shot right up in the underdamped case. There, I got it out. And so What about the critically damped case? What's going on with the critically damped case? Well, the critically damped case is just this kind of perfect scenario where we have current flowing in the clockwise direction, a voltage induced across the inductor, positive here, negative here. So it's trying to overcharge the capacitor, and as a result, it's helping to charge the capacitor a little faster than it would normally charge. However, the voltage across the inductor decays, the rate of change of current is such that the voltage across the inductor decays at exactly the proper rate for the voltage across the capacitor to just shoot up a little bit extra quick thanks to the inductor, and then just kind of taper off nice and flat, and then gracefully approach that 3-volt steady state value. So it's just the inductor and the capacitor are chosen in such a way as they just sort of perfectly act in concert, and there's no sort of oscillations. And so, from a circuit design perspective, you could ask yourself, okay, well, big picture, what do I want? Do I want an underdamped circuit? Do I want an overdamped, critically damped circuit? And the answer, of course, as always, is it really depends on your application. As we're going to see later on in this module, when we talk about oscillator design, we want underdamped. An oscillator is a special circuit that creates a varying voltage signal, often used to clock digital circuitry, for example, or used in radio circuits. And so in that case, we want to design our circuit to be as underdamped as possible. If we are just designing some kind of power supply where we want just a nice sort of steady output voltage level, we would want probably critically damped, right? Because we want to get up to our voltage level as quickly as possible, but we don't want to have any ripples or oscillations. Overdamped would be, I guess, maybe adding a certain factor of safety to that. Somewhere you're really going to see this type of damping come back is also in control systems. And control systems are interesting because we're not going to talk about them here in this course because we're just focusing on electronics here. But a control system is typically the combination of electronics and some sort of physical thing, like a motor or a spring or a tank that you're trying to heat up or something like that, control the temperature in it. And once you sort of incorporate the differential equations for the response of the physical thing that you're trying to control with an electronic controller, you will often find that you have a second order differential equation that could be underdamped, critically damped, or overdamped. And typically when you're designing a control system, you don't want to have oscillations, right? Like imagine you're designing the cruise control for a car. You don't want to be like overshooting your desired speed and undershooting constantly. You want to just converge to that speed. And so in that case, you would typically try for a critically damped system, something that responds as quickly as possible, but doesn't go through any unstable oscillations. Okay, so the next thing I want to do is look at the source-free RLC response. And again, the source-free response is when we switch in a voltage supply, we let, which is modeled as a step function, and we let our a lot of time pass, so all of our voltage levels kind of converge to steady state values. And then the source-free response is when we basically disconnect or switch off that input supply and switch our input voltage back to 0. And so I want to try to take a few shortcuts here with the RLC circuit, just because the algebra is a little more complicated, and we've done really a lot of work to try and figure out what the step response is. I kind of want to recycle that work here. So I want to maybe sort of take a few shortcuts and use our step response to figure out our source-free response as well. And these shortcuts are going to be based on a couple of observations. The first thing is that let's think about a situation where we've had our our DC voltage source, we've switched it in, and a lot of time has passed. And so basically all of the transient responses have died out, and we only have constant DC levels in our circuit. Well, we know that, under DC conditions, the inductor behaves, the ideal inductor anyways, behaves basically like a short circuit. And we know that the ideal capacitor behaves as an open circuit. And so what I want to do is I want to take this circuit and replace the inductor and capacitor with, a short circuit and an open circuit, right? Which is how they would behave once all of the transients have settled out and we're at our steady state. So we still have our voltage source, Vs. Our resistor is still there. Our inductor, however, I'm just going to replace with a wire because it's a short circuit at DC. And our capacitor, I'm just going to replace with an open circuit. And so obviously, because we've broken our circuit here, no current can flow in the counterclockwise direction. That means the voltage drop across the resistor has to be 0 because V is equal to IR. So if I is 0, then the voltage across the resistor is 0. There's no voltage drop across this inductor because it's a short circuit. And so if the voltage at these 2 points is equal to Vs, then the voltage at these 2 points is going to be equal to Vs as well. And so therefore the steady state response of our circuit is just equal to our source voltage. And we know that, right? I mean, we saw that in the step response module previous because everything was converging to the 3 volt level. So therefore, our output voltage is equal to Vs at steady state. So we know that our source-free response is basically, it occurs when we switch our voltage supply off, or we switch from, Vs down to 0. And so we have some input voltage, Vi. We're at Vs, and then at some point we switch our circuit off, right? And we switch down to 0. And so I'm going to represent this as Vi is equal to a constant Vs minus a step function equal to Vs, right? So we started at Vs, and when the step function kicks in, we go down to 0. Now, the Laplace analysis doesn't really like constants like this very much. So what I'm going to do instead is I'm going to kind of maybe cheat a little bit. I'm going to just do my analysis for a negative step function. And then when I have my answer, I'm going to add a positive Vs to the answer because the circuit is linear. And when we do that, we can basically use our step function results that we developed in the previous module, except that our input is minus Vs now than plus Vs, and it'll just save us a little bit of work. Okay, so let's try this idea out for the critically damped case. Where's my eraser shavings here? And so these are just the equations from the previous module, nothing new here. So this is the time domain response for the critically damped case. So we've got a constant term, we've got an exponential multiplied by time, and we've got just a regular exponential. This is K1, K2, and K3. These are the expressions that we solved for. And we know that alpha and omega naught are equal, and they're equal to 1 over root LC. And so just to kind of show how our shortcut's going to work, I'm going to actually I'm actually going to put this equation in terms of L and C. And so 1 over alpha squared, if alpha is equal to 1 over root LC, that's just equal to LC. K2 is just equal to minus root LC. K3 is equal to minus LC. You'll notice the one difference in our equation up here is there's a negative sign in front of the Vs because we're dealing with a negative step function. And so if we sort of put all this together, our output response to our negative step function we've got LC, so you can see how the two terms are going to cancel there right away. Negative root LC t e to the minus alpha t, and then minus LC e to the negative alpha t. And then if we go through and we cancel out these LC terms, we have negative Vs plus Vs over root LC t. I think that's right. And then we're not quite done because this is the response to the negative step function, and we said that our shortcut was going to be to solve this step response and then just add an offset of Vs to it because we had to add an offset to our input, so we're just going to add an offset to our output. And so what happens is these two terms cancel. And then we have two positive terms that are, well, this term, when t is equal to 0, this term is equal to 0. However, when t is equal to 0, this term is equal to Vs. And so what we're going to see for the source-free response, for the critically damped state, we're going to start at Vs. Sorry, that's kind of jumbled in there. Let me do a better job of that. So this is our voltage level Vs. This is a plot of the output voltage as a function of time. So at t equal to 0, this term is going to be equal to 0, but this term is going to be equal to Vs. So we start out here. And then if we plot this equation out or we simulate it in space, it looks like this. And this is kind of what we would expect. So remember our step function looked like this. You know, we sort of had a steady state response of Vs, and then our transient response was this kind of exponential characteristic. And the source-free response, when we turn off our voltage source, starts out at Vs, and then we get the same sort of exponential type transient response. And this is consistent with the first order equations that we looked at, the RL and the RC circuits. The transient response was basically the same. The only difference between the step response and the source-free response is that in the step response, we're starting at 0 and then converging to our source voltage. And then for the source-free response, we start at the source voltage and then we converge back down to 0. So this is kind of what we would expect. So we can see here, and hopefully you can see that we've we've saved ourselves a little bit of work, right? Because we've just recycled our step response solution with a negative step value, and then we've offset our result by Vs. And again, the purpose for that is because we're modeling our input as a negative step plus a constant. And so if we solve just for the negative step initially, we still have to add in that constant afterwards. So the output, as we've seen, the output voltage expression for the under and overdamped responses is the same, even though for the underdamped response we're dealing with complex numbers and for the overdamped response we're dealing with real ones. The overall expression is the same, so the step response, or sorry, the source-free response is equal to our offset of Vs plus the response to the negative step function and I've dropped the step function there, so just to be clear, this is only valid for time greater than or equal to 0. And it's a little bit of a pain, but you can show, and I won't bother doing it here, but you can show that basically the minus Vs over LC times K1 is just equal to Vs. So this offset and the first term here are going to cancel out. And this ends up being equal to negative Vs over LC K2 e to the R1 of t minus Vs over LC K3 e to the R2 of t. And these negatives aren't a big deal because, you know, it turns out that these K2 and K3 values are also negative. So these end up being positive terms that at t equal to 0, both of these two terms added together end up being equal to exactly Vs, and then they decay in, for the overdamped case, they decay exponentially, and for the underdamped case, they decay in kind of an oscillating fashion. And so we'll switch over to MATLAB and we'll see what that looks like. Okay, so just looking at the source-free response MATLAB script, we have the overdamped, critically damped, and underdamped cases. The component values are the same as in the step response. The calculation of alpha and omega are the same. The calculation of the roots are the same. The calculation of the k values are the same. The only thing that's different is the expression for the actual output voltages here. So basically what I've done is I've put a negative sign in front of them and I've removed the K1 term. Because basically that K1 constant term is the term that gets canceled out when we add our offset to the response. And so the overdamped response was negative Vs times the summation of the K2 and K3 terms. The critically damped response, you can compare it to the notes and it's the same equation. Same with the underdamped response. And so if we plot all of these together, on the x-axis, I didn't label it in the script, but on the x-axis we have voltage, on the y-axis, or sorry, on the x-axis we have time, on the y-axis we have voltage. And so all of the circuits start out at 3 volts because that's our steady state voltage level. The overdamped response, its transient response, we can see has the same sort of exponentially decaying characteristic that we saw from the step. The critically damped response decays more quickly, right? Just like it rose to the steady state voltage level more quickly. and the underdamped case decays extremely fast, but then actually goes negative. And the reason for that is, again, the inductor in the circuit working to try and maintain that flow of current, basically. So you can kind of go back to my explanation at the start of this module when I talked about the step response, apply it for this source-free response, and you'll see that it's basically kind of the same mechanisms working back and forth. So the last topic I want to talk about in this module is using an LC circuit to design an oscillator. And so an oscillator is basically a circuit that creates a voltage wave, like a sine wave, that oscillates at a certain fixed frequency, and oscillators are used to clock digital circuits, to drive radio circuits. They're basically sort of the clocks that exist inside all of our electronics. And as I mentioned earlier, oscillators are made using circuits that are specifically designed or intentionally designed to operate in the underdamped mode, or at least that's one way to make an oscillator. And so we know that in the underdamped case, we can write our roots as follows. So when alpha is less than omega naught, we've seen that our roots, R1 and R2, can be expressed as minus alpha plus minus the square root of negative omega naught squared minus alpha squared. Or in other words, plus or minus j omega d. And omega d is the damped natural frequency. Now, we went through this a little bit earlier on, but in the underdamped case, we have a complex exponential, and essentially the real part of our root creates the damping, and the imaginary part of the root creates the oscillation. So e to the r1 or 2 multiplied by time is equal to e to the minus alpha multiplied by e to the plus or minus j omega d. And this causes, as we've seen, the oscillation. And this causes the damping. Now, in our circuit response that we've seen so far, the damping was fairly pronounced. So we saw, just a few cycles of oscillation, and then we converged basically to our steady state response. Now, if we're designing the circuit intentionally to oscillate, we don't want, or we want to have as little of damping as possible, right? We want to keep our circuit oscillating ideally forever. And so we know that alpha is equal to r over 2L. And the way that we would eliminate damping is ideally we would have an alpha equal to 0, and we would achieve that by setting the resistance in our circuit equal to 0. And this makes sense because earlier on we were talking about how it's the resistance in the circuit that basically steals energy from, as current is sort of tossed back and forth between the inductor and the capacitor. And so if we want that sort of exchange of current to keep on going between the L and the C, we would want ideally to remove that resistance so there's no energy being dissipated in the circuit in the form of heat. So we're not going to get a resistance of 0, but let's see how close we can get. So if we look on DigiKey, let's say we want to make an oscillator using sort of a surface mount inductor, and when I did a very quick search on DigiKey, I put in surface mount for my package type, and I found a range of inductors, and the one that I'm going to use had So consider an inductor of, I found one with a 10 microhenry inductance and a series resistance, or winding resistance, of 10 milliohms. And that sounds pretty small, right? I mean, milliohms, normally when we intentionally put a resistor in a circuit, we're dealing with, at least a few ohms. So that seems promising, right? Seems small. And let's say we want our oscillator frequency to be 1 megahertz. So we know the value of our resistance, we know the value of our inductance, we know our oscillation frequency. Now we need to solve for the capacitor that will give us our 10 megahertz oscillation. And we do that by setting omega d, our damped frequency, equal to 10 megahertz and then solving for C, basically. So we know that omega d is equal to the square root of the natural frequency, omega naught, minus the Neper frequency, alpha, or the Neper frequency squared. And if we substitute in our component values, this is 1 over LC minus R over 2L squared. And so if I solve in terms of capacitance, we have capacitance, which is equal to 1 over inductance times the damping frequency squared plus R over 2L squared. R is equal to 10 milliohms. L is equal to 10 microhenries, and omega d is equal to 2 pi times 10 to the 6. And don't forget the 2 pi, because otherwise your circuit won't work the way that you expect. And so if we plug in these values, we get 2.533 nanofarads. And so let's plug this into our underdamped circuit response, our source-free circuit response in MATLAB, and see what it looks like. Okay, so we've got a MATLAB file called Oscillator, and we've got our 10 microhenry inductance, our 10 milliohm resistance, and our 2.533 nanofarad capacitance. Same old equations as before. I actually don't need K1 in here because there is no K1. And when I run this, perfect, right? It looks great. So we start out at 3 volts. We go down to minus 3 volts. We come back up again at exactly 1 microsecond. So our period is correct. And when we zoom in like this, it seems like the 10 milliohm resistance isn't causing us any trouble at all, right? It seems like we're just totally going along on, without any really measurable or significant damping. However, we're only looking at 10 microseconds. Let's zoom out and take a look at a whole millisecond. So when we do that, we can't see our oscillation. It looks like a solid block, right? Because our waveform is oscillating so fast that we can't see it when we zoom out like this. But we can see that even after just 1 millisecond of operation, we've already decayed from a peak-to-peak voltage of 3 volts to a peak-to-peak voltage of less than 2, right? So clearly, when we, if we want to run our circuit for a while, this 10 milliohm resistance does start causing us problems. And this really gets even worse when you actually want to use the oscillator for something, right? So like the whole point of an oscillator is to hook it up to something and have it drive a circuit that needs a clock. And even though most logic circuits, they have a very high input impedance, so they don't draw a lot of current, they do draw at least a little bit of current. And so when you hook up some kind of load resistance to the oscillator, the voltage waveform is going to decay even faster. And so the solution is to not design an oscillator this way, basically. So most practical LC oscillator circuits have some kind of active component, like a transistor in it, that will switch back and forth and add energy to the circuit kind of on a continuous basis. And not only will that overcome any resistances within the circuit, it will also help when we want to hook the circuit up, the oscillator up, to actually drive some kind of load.